is an entirely different video than I thought I would be making today, but that's completely okay. What we've got here is something called an Atwoods machine. And an Atwoods machine is really just a pulley that has no mass in our case, so no mass for the pulley, and an ideal rope. So also a massless rope that doesn't stretch or compress. And it's connected, I guess a rope is connected over that pulley, and then we hang a mass from each side. And what we're trying to do is figure out what the acceleration of this system would be when mass 1 is 6 kilograms and mass 2 is 4 kilograms, and then find a tension in that rope. And I'm bringing this up because I realized with our class that we have different levels of understanding of this as we walk into here. Some of us have seen this before and really grasp it and remember it from the past. Others, this is completely new. Okay, so we want to figure out how to do this. All right, so the first piece is I want to find the acceleration of this system. Well, there's two different approaches you can take because there's three different systems that we can use as we try to do this. The first system we could study is just mass 2. And so we could draw a free body diagram for mass 2, which I would suggest. The second one we could look at is mass 1. We could look at just this mass and draw a free body diagram for it, and I would answer that. And the third one is to draw both masses, M1 and M2, and what, oops, I switched those two, M2 and M1. And what I'm going to do with this is I'm going to take those two ropes, and it's kind of like I'm going to bend those ropes out flat. Because if I think about it, as I think about what gravity is trying to do with this, gravity is trying to pull this mass down. It's trying to pull this mass down. So those two forces are opposing each other. So I'm just going to take this and flatten it out and draw it as though I have gravity pulling this way on M1 and gravity pulling this way on M2, and leave it like that. Okay. Let's do a little erasing there. All right. Among other things that I think we need to understand, a lot of us don't quite understand tension. And so that's the first place I actually want to begin. So I guess an aside is, let's do an aside. Is the force of tension, so is that tension force? And then I want to know among these choices, is it A, tension is equal to 60 newtons? I guess I'll just kind of list all of them. And you're just going to pick which ones apply. In some cases here you'll be like, well, they can't both be true, so yeah, that's sort of obvious. Is tension equal to 60 newtons? Is tension equal to 40 newtons? Is tension greater than 40 newtons? Is tension less than 40 newtons? Is tension greater than 60 newtons? And is tension less than 60 newtons? Okay, so take a second, think about that, and pick all the ones that you think apply. So pause the video and think. All right, maybe a piece to help you along your way with this would be to draw some free body diagrams. So we'll select these in just a second. So if I'm thinking about M2 and M1, the first thing I want to think about is what direction things are going to go. Since M1 is the heavier mass, I think it's going to accelerate downward. Since M2 is the lighter mass, I think it's going to accelerate upwards. Okay, because I think this whole system is going to go like that. So if I'm thinking about those two things then, this block has a tension acting up on it. We'll call that tension 2. We'll call this M2G. This block has a tension acting up on it, tension 1. And we'll call this M1G. And when I asked about tension, I didn't say which tension I'm thinking of. Well, that's because I know something about this tension that I'm realizing you might also not know. So I promise we'll come back to this and we'll get to these, but I just keep thinking of all these things you may or may not know. If I was to take a system of masses like this, here's M1, here's M2, and they're connected together by a rope, and then I'm going to apply another force F this way, so that the whole system accelerates in that direction. All right, well, if that's the case, that's just the worst A ever. Erase. If that's the case, we're used to drawing free body diagrams for mass 1. We're used to drawing for mass 2, but what we're not used to doing is drawing free body diagrams for the rope. So I'm going to do that real quick. Acting on the rope, I'd have the force of mass 1 on the rope, and I'd also have the force of mass 2 on the rope. Now, what I'm used to describing in these problems is tension. But tension, we define as just the force of that a rope applies to something else. So the force mass 1 applies to the rope is also equal to the force that the rope applies on M1. Well, that's just another name for tension. So I'm going to call this tension 1. And similarly, the force that M2 applies to the rope is the same as the force that the rope applies onto M2. So that's another name for tension rope, so I'm just going to call that tension 2. Now, if I do net force equals MA for this rope, so let me search that down. If I do net force equals MA for that rope, okay, I know that I have tension 2 acting to the right in the direction this thing's going to accelerate, and I have tension 1 opposing, and that's going to equal the mass of the rope times acceleration. Now, in this situation, if my system is M1, M2 in the rope, I know I have an unbalanced external force F acting on that system, so the whole system is going to accelerate to the right. Okay, which means the rope also is going to accelerate to the right. So I know this acceleration is not 0. However, our ropes are ideal ropes, which means that the mass of that rope is 0. Okay. Well, if this side of the equation equals 0, if tension 2 minus tension 1 equals 0, then that tells us that tension 2 must equal tension 1, which means that the tension in the rope is the same throughout that rope. All right, that's a big deal, because that explains why, as we were looking at this, when I said that this was a massless rope, why I just said, is tension these things, and I didn't say tension 1 or tension 2. It's because the tension in the rope is the same throughout when we have a massless pulley and an ideal rope. Okay, and so far that's all we've got in our kinds of problems. All right, so now for the big reveal. What does have to be true about tension? Well, based on our free body diagrams, tension cannot equal 60 newtons, because this force of gravity is 60 newtons, and if tension, which now I'll just write as tension, not T1 and T2, but just tension, if that tension is 60 newtons, then this block isn't going to accelerate up or down. Well, we know that's not what's going to happen. This system's going to go like this, so the tension can't be 60 newtons. Similarly, the tension can't equal 40 newtons. If it did, then this block wouldn't accelerate. It would stay right where it is. And we know this system's going to accelerate because this heavier mass is going to fall and the lighter mass is going to rise. Well, what is true? Well, to make this thing rise, I know that this tension, to make this accelerate upwards, this tension has to be bigger than M2G. So tension's got to be bigger than 40 newtons. But the other thing that's true is that for this block to accelerate downward, I know that tension has to be smaller than the 60 newtons that are pulling down, so tension has to be less than 60. So my tension's got to be somewhere in between these two weights, and that's going to be true in all these Atwoods machine problems. That's our first concept we need with this. All right, going forward, solving this thing. So to get the acceleration of this system, I really think that this is our easiest one to do. And in that setup, we just say that the net force acting on this is M1 plus M2 times A. Okay, the net force on that system is just going to be the weight pulling us in one direction. That's the weight pulling this way, M1G, minus the weight opposing, so the weight trying to pull us the other way, which would be M2G. And that's going to give us what's left over, which is M1 plus M2 times A. Solving for acceleration, I'd get M1G minus M2G all over the sum of their masses, M1 plus M2. And so as I plug stuff in, this looks like 60 newtons, this looks like 40 newtons, so 60 minus 40 is 20 newtons. And I'm going to divide that by the sum of their masses, which is conveniently 10 kilograms. So this system looks like it's going to accelerate at 2 meters per second squared. Now notice I'm just calculating the magnitude of the acceleration, not the direction, because one of these accelerations is down and one's up. And that's why I always use net force equals MA, not as a vector equation. All right, the second thing I want to do is find the tension of that rope, so I'm just going to choose the M1 system and say that net force is equal to M1 times A. Again, all these masses have the same acceleration. The net force on that one would be the larger force, gravity, minus the opposing force, tension, and that equals M1A. And I have to pick one of these two systems because I need a system where tension is external to that system. I'm going to solve for tension, so I get M1G minus M1A is equal to tension. And when I plug in some numbers, M1 times G, that's 6 kilograms times 10 meters per second squared, so 60 newtons, minus M1 times A, that's 6 kilograms times 2 meters per second squared, so that's 12 newtons, is equal to the tension. That tension just equals 48 newtons. All right, I think we should do another one or two of these for homework, so that's our sample video. Hopefully that helps, and good luck on your homework.